Okay, good afternoon, everybody. Welcome. Welcome to so many people from across the world. We may have close to 80 countries here on this call. People who may be in the morning, in the afternoon, the evening. I hope you're all doing well. Our thoughts are also with those that unfortunately are not able to join due to the difficult circumstances that they are in. And in fact, if we think about our topic of astronomy, the beautiful night sky, that is something that even in these difficult circumstances, these trying circumstances that are across the world, we are still sharing. And in fact, people are still sharing that even with social distancing. And we can continue to enjoy the beautiful night sky. Just this weekend, the beautiful sturgeon moon that you see here over Greece, and that is providing both inspiration, perspective, a sense of passion, dreams, and also a sense of tolerance that the night sky still instills in all of us. And so I think we're fortunate to be here in this topic of astronomy that unites us all here in this meeting. So a few organizational matters. First of all, this meeting is being recorded. Those of you who are on the Zoom, there's a limited number of people here on the Zoom. Please raise hands if you want to ask a question. Please put your speaker on mute. Comments can be in the chat or on the Slack. And comments should be formulated in a respectful way. This meeting is under our IAU Code of Conduct. Now, why are we here? Why are we here today? Well, actually, we were supposed to be in Busan, in this beautiful conference center here, Bexco, that is in Busan in South Korea. Exactly this week, that's where we were going to be there. And unfortunately, due to the pandemic, that is now moved to 2022. But we really hope that in 2022, we can get together and enjoy both the science and maybe also leisurely on the beach, talking about the science on August 2 to 11, 2022, when the meeting will be in both face-to-face and hybrid mode. But a part of the General Assembly is always the business sessions. And these need to happen every 3 years. And so for this, quote, boring part of the General Assembly, that is what we are here for today. But to give you also a sense of the flavor of the General Assembly, we decided to mix in some of the elements of a General Assembly, science talks, and also learning more about the other elements that make up the IAU Today. And so in the first sort of 1.5 hours before the General Assembly starts, we have a set of high-level science talk by both senior and junior prize winners. You get to meet the IAU offices, and we will have brief reports from our executive committee working groups. And so this is really to give you a flavor of the GA and also what the IAU actually does today. Note that some of these reports will be very brief, but you'll get to hear more about it at the General Assembly next year, when all of the offices and executive committee working groups will have dedicated 1 to 2 day meetings. So what is the IAU? Well, the IAU is actually the worldwide union of all professional astronomers, PhD level and above. And the main mission is to promote and safeguard astronomy in all of its aspects through international cooperation. And this means really worldwide cooperation. And these days, that's much more than just a research component. It's also communication, education, and development. And that's what you will see reflected here in this program. We are 102 years old, founded in 1990. And we have now more than 12,000 members with more than 100 nationalities and 82 member countries. In fact, what we do, you can find that in the IAU strategic plan that was approved at the General Assembly in 2018 in Vienna, and that is now being implemented. You can find it on our website that I can highly recommend you to go to if you are not familiar with it, because you will find lots and lots of information on it actually about all the aspects of the IAU. So the traditional function of the IAU is to bring people together worldwide, to share astronomical knowledge. And we do that still through our 9 symposia per year, 1 regional meeting per year, and our General Assembly only once every 3 years. But we also have an increasing number of co-organized meetings. Take, for example, the communication of astronomy with the public. That was actually a virtual conference this year with more than 1,000 participants. So showing the growing community also in that field. All of our 2020 symposia, except a couple, have been actually postponed, the regional meetings as well, and the GA also. So 2022 to 2023, when we hope that our world will be back to some sort of normal, is when many of these meetings will take place. Now, how is the IAU actually organized? Well, we have our divisions and commissions. All of you are a member of at least one division, going from fundamental astronomy to galaxies and cosmologies. But there are also 35 commissions and 53 working groups. Now, more than 100 groups altogether. So there are a few of these working groups that are actually special and that report directly to the executive committee because of their important function. One of them is the Women in Astronomy, another one junior members, Equity, Inclusion and Diversity, the Dark and Quiet Skies, which of course has been very active in the last couple of years due to the satellite constellation threat and the global coordination of ground and space-based astrophysics. And so you'll get to hear very briefly from each of these offices to get to know the people involved. So the knowledge advancement is the traditional role of the IAU. But then there are all the other aspects that have been added. The Office for Young Astronomers that has been organizing the EASIA schools already since 1967, now hosted by the Norwegian Academy of Science and Letters. The Office of Astronomy for Development since 2011 in Cape Town, joined with the NRF. The Office of Astronomy Outreach in Tokyo, jointly with NAOJ. And then the newest office, that in Heidelberg, the Office of Astronomy Education, jointly with Max Planck. And so again, these are now having a very important function within the IAU structure. And that is why you get to hear from each of them in the coming 2 days, today and on Thursday. A very important part is also that all of these offices actually now have worldwide networks. And this is the strength really of the IAU, that we have these connections now, not just through our scientific networks, but also through these outreach, education, and development networks across the entire world. And that has already been proved to be very important also in the context of the 100-year celebrations, which we had in 2019, and which were actually a trigger to bring, especially on the outreach side, a lot of people together. And so if you want to read more about that, I will tell them some more about that in the business session, but you can also browse through the report that is actually posted on the IAU website, and where we were able to reach many tens of millions of people worldwide. Okay, so I'll stop here and just say that I hope you will enjoy this IAU taster, so to say. It will be a mix of live and pre-recorded presentations, pre-recorded because some people are in time zones that do not quite match with the daily business, or they are in time zones or in regions where hurricanes are actually threatening power outages. So that is why we have a mix of them. Good, and so I'll stop actually here and actually introduce our first speaker of today, and that will be Volker Springel. The IAU is actually fortunate to have very good connections with the foundations that sponsor the major prizes in astronomy. And its relation with the Gruber Foundation dates back already to 2001, and the IAU is proud of its Gruber Cosmology Prize winners. So in the past triennium, these have been Nick Kaiser and Joe Silk, Lars Heimquist and Volker Springel, and most recently, Mark Kamionkowski, Otter Seljak, and Matthias Saldarriago. So today, Volker Springel from the Max Planck Institute for Astrophysics is with us live to give you a flavor of the increasing importance of cosmological simulations in understanding our universe. Volker, this floor is yours.
Thanks a lot, Evine. I hope you can all hear me well. It is a real great pleasure for me to be allowed to talk to you here in this pre-meeting of today's business session of the IAU. And I decided to talk about a topic that's close to my heart, namely simulations of black hole feedback in galaxy formation. I find this is a particularly fascinating topic because it's from the start not really evident that supermassive black holes at the centers of galaxies have much to do with the evolution of the galaxy as a whole, because the black hole is very much smaller. It ultimately, influences conceivably the galactic center, but why should supermassive black holes be a major player in galaxy formation? Now, there are a lot of observational arguments why this is the case, and I think Andy Fabian on Thursday will in fact show you a lot of this evidence. But there are also theoretical arguments why there might be a connection. And one of the most basic one that I find fairly convincing is if you look at the energy that is liberated by supermassive black holes in the form of quasars over the lifetime of the universe, you arrive via simple estimates at a total energy that is comparable or even larger than the energy released by all the supernova explosions throughout the cosmic history. So, and because supernovae are, of course, regulating the star formation in galaxies, we see here that there's another source of energy that's at least comparable in magnitude. And if this energy that is released at the centers of galaxies can somehow couple to the galaxy, then you might have another player that influences galactic evolution in decisive ways. And that is really the million-dollar question. We don't really understand very well yet how this energy liberated by the AGN, which we call the AGN feedback, is ultimately coupling to the interstellar gas and how it's regulating galaxy formation. And I work on this subject with colleagues for a while now, using numerical simulations, trying to understand aspects of this problem. And in fact, I've started to work on this about 15 years ago, together with Lars Hörnquist and Tiziana Di Matteo. And at the time, we introduced for the first time a modeling of supermassive black hole growth and associated feedback at the centers of galaxies. And we looked at galaxy mergers as a model system where potentially the tidal torques are thought to drive a lot of gas in the centers of galactic nuclei, like you see in this image sequence on the right. And the idea is that then during such a galaxy merger, the quasars will be fed by a lot of gas, will start to grow exponentially in mass, and then their luminosity will also grow in magnitude until eventually they become so bright that the energy output does something to the gas. In terms of physical modeling, it is very simple what we've done here. We assume that the black holes grow with a simple only rate prescription at the center of galaxies, and an even bolder assumption then was that we assume that some of the liberated energy from the accretion, this is about 10% of the rest mass energy, is coupling thermally to the galactic center, so it's just heating the gas there. But with this simple prescription, we obtained a phenomenology in these simulations that is quite interesting, because the quasars then are triggered by a galaxy merger, grow a lot, and eventually they release so much energy that the dust and shredded environment in which they are embedded is blown out. They become visible as bright quasars for a brief time, and then the activity shuts down because this quasar activity is sort of suicidal. The quasar cuts itself off from further gas supply and leaves behind a red and dead elliptical galaxy. Now, while this is a nice sort of brush, coarse picture of how a quasar might be triggered and how it's growing, this major merger paradigm is that what we've learned in recent years is certainly not the only growth channel for large supermassive black holes. Secular processes might also trigger quasar activity and also minor mergers. And there is another environment where we have direct observational evidence, namely in galaxy clusters, that there must be a direct impact of the supermassive black hole sitting at the centers of the BCG galaxies and clusters, because there we see X-ray cavities, for example, that are directly tracing the radio galaxies' activities. And Deborah Shiyatsky introduced a first simulation model in where these radio bubbles are triggered by episodic black hole activity in galaxy cluster centers. And she could show that this is indeed a way to curtail also in these simulations the cooling flows that you would otherwise expect in these galaxy clusters. This activity, however, is a very different one, certainly, from the major merger scenario that I just showed you. Now, in recent times, we've turned to much larger and more comprehensive simulations where we follow full pieces of the universe directly after the Big Bang. We start the calculation there, use the cosmological initial conditions that we see at the CMB, and then track structure growth forward in time, both in the dark matter sector, but also in the cosmic gases. And these simulations, they track galaxy formation with a lot of detail. So they follow, for example, the radiative cooling of gas, then the star formation in galactic centers, and also the black hole growth and its activity. Now, most recent models we call illustrious TNG, and I will tell you a little bit more about this in a minute. And with respect to the black holes, we incorporated here all the lessons we had learned earlier. We came up with a novel model that is more sophisticated than the previous one to follow the growth of black holes, and in particular, their energy release and how this influences galaxy formation. And we have adopted still two different types of modes in how these quasars grow. When they are fed very rapidly, they are in so-called quasar mode, and their feedback is then thermal, like in these older calculations. While if the accretion activity is very low, this is the radio state or low state of such an AGN, then we invoke kinetic feedback. And this was motivated by observations of so-called red geyser galaxies that are apparently kept red and dead by repeated low-level quasar activity that is, for example, appearing in the form of winds that are driven by the accretion disk of these systems or by small-scale jets. So these observations were something that we could previously not reproduce in our simulations, but with this refined model, we now can. In fact, these modern cosmological simulations, they produce shapes for galaxies much like the shapes we observe. Here you see a couple of example images from illustrious TNG. On the left, the gas distribution in a sample of disk galaxies. On the right, the stellar distribution. And interestingly, the morphological mix produced by these calculations is quite close to what we actually observe. Also, the sizes of these galaxies and the stellar masses are to first order in relatively good agreement with observation data. And this is also true at different redshifts. And one thing that was really made possible by this revised AGN feedback models is that the color distribution of galaxies, the so-called bimodal color distribution and emergence of a red sequence is for the first time predicted also quantitatively correctly as a function of stellar mass. Here, this is shown here in this comparison to the Sloan Digital Sky Survey. So that was a nice success of these newest models. And at the same time, the galaxies are also distributed in space, like we see the clustering of galaxies in the real universe. Here's a comparison of the clustering signal of red and blue galaxies of the simulation models compared with the very accurate Sloan Digital Sky Survey data. And while the match is not perfect, it is actually relatively gratifying, certainly better than we expected. But maybe, and that's coming now to the heart of my talk, I'm going to show you a few maybe more surprising things that we realized in recent times about these models. Namely, and this is that there are certain phenomena that we describe as the emergence of larger scale phenomena that you would not necessarily expect maybe from the primitive modeling that we ultimately do. Because you need to be aware that the actual physical details of the accretion flows onto the black holes, those are unresolved in these cosmological simulations. We simply lack the spatial resolution to treat all the physics in an ab initio fashion. Instead, we need to make very strong simplifying assumptions. These are sometimes called subgrid models. And in particular, the feedback, hence that is the energy output of these black holes, is injected in an isotropic fashion in the calculation. But nevertheless, you then see bimodal outflow patterns. This is illustrated here on the right in this image sequence around a galaxy that has a strong phase of its activity of kinetic feedback of its central supermassive black hole, and it drives a bimodal jet-like wind, even though there are no jets directly modeled in the simulation. So that is generically happening in these calculations, that the quasar feedback seeks the path of least resistance and then drives these bipolar outflows. And here's another finding recently that illustrates that some aspect of the specific assumptions we make about the HN feedback are potentially puts us on the right track. At least if you compare the so-called quenching phenomenon in galaxies with between observations and the new stimulation models, you find some interesting agreements in certain trends. And this is shown here in this nice recent paper by Erica Nelson. She looked at HST candles observation of galaxies, very high resolution, spatial resolution observation that allow in particular the measurement of the specific star formation rate as a function of the distance from galactic center. And if you stack different galaxies, you can make very accurate radial profiles of the specific star formation rate of these galaxies. And what she's then done, she's, after confirming that the star formation main sequence is agreeing between observations and this data, this is shown in this left panel, she looked at galaxies below, right on the star formation main sequence and above the star formation sequence. And this group of galaxies below it, these are galaxies we think that are in the process of being shut off, being quenched by the central AGN. What you see in these maps of the specific star formation sequence is that there's basically a hole in specific star formation at the centers of these galaxies. And we interpret this as a trace of the phenomenon that the star formation is shut off inside out. So the AGN from the center propagating to the outer parts is turning off the star formation in these galaxies. And this is something that we see both in the HST data and also in our TNG simulations alike. So there's a very good agreement, and we can prove that it's really the AGN that's doing this by disabling AGN physics in our simulations, or looking at older simulations that were lacking the specific kinetic feedback model, and they don't show this particular signature. And here's another particularly interesting finding in a paper.
One more minute.
Okay, that recently appeared in Nature by Ignacio Martin Navarro. He looked at the fraction of quenched satellite galaxies in Sloan data as a function of the position angle of these satellites, as you see in the sketch, relative to the major axis of these galaxies. And what he interestingly found is that there is a modulation of the fraction of quenched satellites with this position angle. There are, in fact, more quenched galaxies in the direction of the major axis and fewer in the direction of the minor axis. If we look at our TNG simulations, they interestingly produce the very same modulation with angle of these satellites. And we interpret this, that this is because the ram pressure stripping of these satellites is weaker orthogonal to these galaxies, hence in the direction of the minor axis. And the density there is actually lowered because of the HN feedback. We can show this again by running simulations that are not including this physics, and then the signal goes away. So we see another indirect evidence for the importance of this. And finally, this is just very briefly, we also see bubbles like the X-ray and Fermi bubbles in the galactic center emerging from this isotropic feedback. So some of the small scale details, how this is done, are actually hidden. And that's what we think the energetics of the HN feedback maybe is of primary importance how this manifests on large scale. So that which is good news for us simulators, because we might not need to get all the details right. So take-home message from my brief talk is, I wanted to show you that black hole physics is actually of key importance in galaxy formation, especially for large galaxies. In our modern simulations, the so-called quenching happens inside out in agreement with the observations. And there are also some more subtle agreements now reached between these theoretical models and observation data, like what I showed you briefly in the SDSS, the quenched fraction of satellites. All of this suggests that we might have some aspects of the backbone of galaxy formation, or at least roughly correct. Thanks a lot.
Okay, thank you very much, Volker, for this fascinating insights into the galaxy and galaxy evolution. We have time for one or two very quick questions. Who wants to have a question of those who are on the call? Let me ask actually one myself. You talked about the shape of the galaxies, and especially now that we see with ALMA and maybe also with JWST, hopefully soon, galaxies already at high redshifts having a very orderly motions and shapes. Does that start to push your models?
Yeah, I mean, that's definitely the frontier. There are some galaxies at high redshift that have, for example, very quiescent rotation, already big disk, cold disks at high redshift. This is potentially a challenge for some of our models. So we are still investigating this, but I think, yeah, so this might be the new frontier where some of our simulations are disproven. You have to understand better why this is.
It's good. Well, thank you so much, Volker. There may be some additional discussion going on in the Slack. Feel free to ask your questions there. In the meantime, we move on to the first office. It's my pleasure to introduce the first office, the Office of Astronomy Outreach, which is actually all about communication. Lina Kanish is joining us from Japan, and she has a pre-recorded video in which you will also meet outreach coordinators from across the world. So please go ahead and start the video.
And here lies our strength through our shared values of. My name is Lina Kanish, and I am the director of the IAU Office for Astronomy Outreach, and we are based at the NAOJ, the National Astronomical Observatory of Japan in Tokyo. It's a pleasure to be here today and at the beginning of this new triennium, after a much troubled period, to say the least. We look forward to what new challenges lie ahead of us, and with the certainty that no matter what, we, the IAU family, will overcome it together. And here lies our strength. Through our shared values of tolerance, respect, international cooperation, they are deeply embedded in our mission of promoting and safeguarding astronomy. The goal of our office, the goal of the OAO, is to engage the public in astronomy through access to astronomical information and communication of astronomy. This goal is implemented through our IAU outreach engagement initiatives with the public and a core network of IAU national outreach coordinators, our NOCs. A vibrant and inclusive global astronomy community of communicators, informal educators, professional and amateur astronomers that through international collaboration are making astronomy accessible to the general public. Our office is about them, is about supporting them, supporting our NOCs that are over 100 spread around the world. So today I want to give word to a few, as time is limited, of course, but today we want to celebrate them. They are the true force of our office that on a daily basis are making a difference in their communities, shedding light on numerous social problems through science communication and critical thinking, and often at the cost of their own safety. Here today, we want to highlight and thank these remarkable human beings. Thank you very much.
Bonjour.
Assalamu alaikum wa rahmatullahi wa barakatuh.
Hola.
아이보원, 와나컴.
Namaskar.
Habari zenu.
안녕하세요.
Konnichiwa.
Mabuhay.
Salam alaikum.
Grüß Gott aus Liechtenstein, hoi miteinander.
Hello.
Gobai hao.
Namaste, pranam, vanakkam, adab.
Hola a todos.
We are carrying out activities to make the astronomy of native peoples more visible to the national and international public, and we are trying to make astronomy more accessible to general public by promoting the communication of science and professional amateur relations.
ENOC allows me to learn from professionals and other amateurs across the world, to have access to a diverse international and national support, and most especially to bring people in this part of the world together to share the same passion and study science beyond our horizons through this unique perspective of science.
We are making astronomy more accessible by promoting communication of science through public engagement, professional amateur relations, and citizen science activity.
As an NOC, I'm also able to get and share with the local public the astronomy resources and knowledge that I gain from outreach efforts around the world.
My role as an NOC allows me to learn about best practices in astronomy outreach and become acquainted to a wide international support group of active outreach implementers, all of which will contribute to a better knowledgeable astronomical community.
Being an NOC allows me to support local communities, to learn from other countries, as well as building network and collaborations with diverse community, as we are all sharing the same passion to build astronomy and science among public.
Continuous connection with OAN is very important. I sincerely look forward to meeting every colleague in the General Assembly in Busan next year.
We are making astronomy more accessible by
public and community outreach,
media interaction,
citizen science projects,
building relations with different people and groups,
and lobbying for astronomical infrastructures and services to support educational and research activities in Nepal.
As a national outreach coordinator, this allows me to learn more and be a part of international support community to make astronomy more accessible for everyone.
Especially like a country in Tunisia where astronomy is absent in university courses, outreach activities play an important role to also show to the people and to the public that this science is really important in our lives.
We make astronomy more accessible by increasing scientific communication through public engagement, amateur professional relations, and citizen science initiatives.
The OAO has built a huge network of astronomy communication professionals and amateurs worldwide. We share our best practices and encourage new collaborations between countries and regions, but also within our own countries. Making astronomy accessible to everyone and inspiring people of all ages is our common goal.
Being a NOC allows me to structure our newborn community of amateur astronomy and share information with others in other countries doing the same. We make astronomy more accessible by disseminating accessible information and opportunities.
As the NOC, I am responsible in promoting and encouraging Malaysians to participate in IAU global outreach projects. Various activities have been carried out involving amateur astronomers, students, teachers, and the general public.
We want to make astronomy accessible for everyone by supporting and helping people who do what they do best, to explain what's wonderful about the universe and make it relevant to people.
As my country NOC, I'm being motivated to seek alternative ways to communicate the astronomy to the public, given that we can't be physically near the people due to the pandemic.
For me, the OAO is a uniting factor for a global community of active and hardworking astronomy outreach people. Over the years, it has not just created networks and opportunities for us to come together, but also given us a confidence to present our work and collaborate with others. Being an NOC gives me a chance to work with similar-minded colleagues and also allows me to learn about their diversity.
The OAO is all about building bridges between the IAU and the global astronomy community of amateur astronomers, outreach professionals, science communicators, and the general public, and through international collaboration to make the science of astronomy accessible to all.
As NOC for Ecuador, I am proud to continue helping and making astronomy to be disseminated and promoted among our children and young people, establishing relationships between professionals and the general public to stimulate the study of astronomy.
Our engagement for astronomy outreach is making people open their own eyes and look around over their own head. Opening eyes and looking around is the beginning of all science and knowledge.
Japanese amateur astronomers have been making astonishing results, such as discoveries of new comets, novae, and supernovae. We are making effort to connect these results to the astronomical research.
Being a NOC helped me to do astronomy outreach in my country, and the OAO office is helping us to make astronomy accessible by allowing our community to participate in international activities, campaigns, workshops around the world that everyone is learning from, including myself.
Wonderful. Congratulations to all the NOCs that actually participated here in this wonderful video. Thank you very much, Lina. I think in view of the time, we'll go on with the next talk, but if anybody has comments or questions to Lina, feel free to actually put them in the Slack where she can answer them. Okay, good. Then we actually go on to the next talk. We go back from one of our offices to top-level science, because we are fortunate that the Gruber Foundation also very generously sponsors annually a few fellowships for young scientists at postdoc level, providing them with $25 to $50 research money. Anupam Bajwa is one of the lucky winners. He did his PhD in India in 2018, then was a Kavli Institute Fellow in Beijing, and is now an ECOA Fellowship in Kasi in South Korea. So truly moving around countries in the IAU spirit. Anupam, we look forward to your talk. The floor is yours.
Thanks, Evin. Hopefully you all can hear me. It's a pleasure and honor to talk about my science here, and I'm going to talk about pulsating stars and their application to the cosmic distance ladder. So I'm interested in a very specific group of pulsating stars that are located within the instability strip on the HR diagram. These include classical Cepheids, which are young POP1 stars, RR Lyrae and type 2 Cepheids, which represent old population 2 stars. Myras, on the other hand, are AGB stars. And all these stars represent different evolutionary states. So they are very useful traces to understand stellar evolution and pulsation. More importantly, these stars follow a well-defined period luminosity relation. Okay. Can you see my next slide?
Not yet. Whoops.
Sorry. There seems to be an issue.
Let's start sharing again. Yeah.
Sorry about that. Yeah, so these stars follow a well-defined period luminosity color relation, which basically comes from the pulsation equation or period mean density equation combined with the Stephan-Boltzmann law. So in a two-dimensional plane, this becomes a period luminosity relation, which makes these stars as stellar standard candles. So classical Cepheids in particular have been used extensively to calibrate the first range of the cosmic distance ladder to determine Hubble constant in the late evolutionary universe. So the plot here shows a traditional Cepheid supernovae distance ladder from the SHOES project. So in the first step, the geometric distances to Cepheids or Cepheid host nearby galaxies are used to calibrate their period luminosity relation, which in the next step is used to estimate Cepheid-based distances to type 1a supernovae host galaxies and calibrate the peak magnitude of type 1a supernovae. Then in the third step, you use the supernovae magnitude redshift relation to measure Hubble constant in the Hubble plume. So as we know, the Hubble constant is one of the most important cosmological parameters because it not only provides the expansion rate of the universe, but also very stringent constraints on the amount and the nature of the dark energy in the universe. So as you probably know, there's an ongoing tension in the Hubble constant measurements. Oh my God. Sorry about this. There seems to be an issue. Okay, fine. So as I'm saying, there's an ongoing Hubble tension in the H0 measurements between the two extreme ends of the universe. So in the local universe, the population one Cepheid-based measurements are quite significantly higher than the H0 measurements in the early universe from the Planck. There is also a discord between population 1 Cepheid-based measurements and population 2 TRGB measurements. So it is extremely important at the moment to understand possible systematics in the measurement of the Hubble constant, in particular in the primary calibration of different stellar standard candles. So I will show briefly some of the efforts that I'm involved in to improve the calibration, primary calibration of these distance stellar standard candles. So classical Cepheids, as I said, have been long used for this purpose, and with recent Gaia EDR3 parallaxes, their calibration is now possible with a percent level precision in our own galaxy. Before Gaia, Large Magellanic Cloud has traditionally served as an anchor of the cosmic distance ladder. And I was involved in a near-infrared synoptic survey of the LMC to do exactly that and obtain near-infrared light curves of hundreds of Cepheids in the Magellanic Cloud. This resulted in an order of magnitude increase in the sample size and the precision of the period luminosity relation. I also investigated universality and the nonlinearities in these relations, which reduces the systematic uncertainties due to the slope and metallicity coefficients in the measurement of the Hubble constant. In fact, the H-band photometry from this survey has been used extensively in the SHOES project to derive this Wesson-height magnitude. As we reach percent level precision, it is important to explore all possible and known and unknown systematic uncertainties. For example, in the galactic calibration, there could be systematic coming from the parallax 0-point offset present in the Gaia data. There could also be residual systematic due to metallicity effects on the Cepheid period luminosity relations. There could also be systematics in the distant Cepheids in the supernovae host galaxies where the photometry may be affected by the crowding and other issues. As an alternative to Cepheids, RR Lyrae and tip of the red giant branch stars are being used to develop an independent population 2 distance ladder. So these population 2 stars are found in all types of galaxies. So they are and they are also located in less extincted and crowded regions. So these are quite useful for this purpose. RR Lyrae are in fact fainter than Cepheids and TRGBs, but they can be used to test and complement TRGB distances. So one of the issues with RR Lyrae distance scale is that their metallicity effects are not well constrained. Theoretical models predict a metallicity dependence that is typically larger than the empirical calibrations. So to resolve this, I started monitoring RR Lyrae in the globular clusters of different mean metallicities. The idea was simple, that if you can somehow get relative or absolute distances to these globular clusters, then you can determine or rather quantify the variation in the luminosity due to the metallicities. So we have already published a few clusters from this analysis, studying their near-infrared pulsation properties. We also published the new calibration of period luminosity metallicity relation, especially using Gaia EDR3 parallaxes. So the plot on the right shows a very strong metallicity dependence in the period luminosity relation, such that the RR Lyrae in the metal core clusters are brighter. We also found a metallicity coefficient that is consistent with the theoretical prediction. And we are also increasing at the moment the metallicity baseline so that we can be consistent with the metallicities of all our LRAs. Just one slide on MIRAs, which are again quite bright in infrared. So they have been used as distance indicators to measure Hubble constant. So I was more interested in max light properties of MIRAs at optical wavelengths. So we looked at the period luminosity relations, and we found that they exhibit quite a smaller scatter than the traditional mean right relations at optical wavelengths. And we attributed this property to the less sensitivity of MIRA luminosity to the unstable water molecules at the epoch of maximum brightness. So these maximum light properties will be quite useful for MIRA distance scale, especially in the LSST era, where we'll get multi-band light curves for these variables in hundreds of galaxies. So instead of a summary slide, I wanted to acknowledge the IAU and Gruber Foundation Fellowship. And I plan to have an education and outreach program, especially in the hills of Uttarakhand, which is a northern state of India where I come from. This also hosts a 3.6 meter optical telescope. So the idea is to promote education and outreach and astronomy education in the isolated villages of Uttarakhand. So this has been postponed due to the pandemic, but I'm hoping, keeping finger crossed for this to go offline in the post-pandemic era. Thank you. I'll stop here.
Okay, thank you very much, Anupam, for a very impressive set of observations, but also showing how to use indeed the Gruber Fellowship both towards research, but also towards outreach. Thank you very much. Is there any quick comment or question from anybody here on the line? If not, then we'll continue the discussion on Slack. I've seen already a few comments on talks coming in there. Please use that to interact with the speaker. So thank you very much, Anupam, and we wish you all the best with your future career.
Thank you.
Good. Then we actually move to the EC working groups. And the first taste of an EC working group, the first one to make its appearance, is actually that on equity, inclusion, and diversity. That is led actually by Amelia Ortiz from Spain. So let's listen actually to Amelia's recording, and she will also be online to answer any questions. So please start the recording.
Hi everyone, it's Amelia Ortiz Gil, and I am going to present very briefly the IAU Executive Committee Working Group on Astronomy for Equity and Inclusion. I am the current chair of the working group, although only for a few more days, and Lina Canas is the co-chair. So the working group has a little more than 200 members by now, and it works in collaboration with some associate members, which provide for the expertise that we as professional astronomers might lack in relation to the topics of accessibility, special education, and inclusion. Our mission is to address the systemic structure, functions, processes, and attitudes that result in the exclusion or restricted participation of underrepresented groups in the field of astronomy. And we do that by researching and developing strategies, tools, and resources that enable equal participation in astronomy at all levels. As we cover a large range of topics which are quite different among themselves, the group has been structured into more specific subgroups after identifying the topics that were more relevant for the community. So we have groups devoted to physical disabilities, as well as others dedicated to minorities, large astronomical collaborations, or gender-related topics. I would like to show you very briefly some examples of specific actions that the working group has led recently, many of them, of course, in close collaboration with the IAU offices. And those include, for example, several actions during the IAU 100th anniversary by contributing to the content of the IAU 100th Inclusive Astronomy website and offering tips about inclusion during the 100 Hours project. Also, we created the Inspiring Stars exhibition. The Inspiring Stars exhibition is a traveling exhibition about inclusion in astronomy and its benefits for the scientific research. It has been shown in venues as different as Vienna, Tokyo, or Thailand, and it will travel next October to La Palma in the Canary Islands. We also have a team working on the development of the Sign Language Universal Encyclopedic Dictionary with the goal of developing a comparative list of astronomical terms in as many different sign languages as possible to achieve the inclusion of the deaf community in astronomy everywhere in the world. We have also organized 2 conferences about diversity and inclusion in astronomy at Colombia and Japan. And an important outcome of the IAU Symposium 358 in Japan was to draft a resolution supporting equity, diversity, and inclusion that has become a springboard to action document to the IAU. The document offers specific recommendations to the IAU in the field of equity, diversity, and inclusion, and recommendations to national members as well, and also for individuals. I will finish here. You can find more information about the working group and its activities at our website, our Facebook group, and at the monthly newsletter that you can find at the website. These are the links, and any member of the IAU can join in by simply sending a request to the IAU at the IAU Info's email. So thank you very much for your attention, and please feel free to contact me directly if you wish.
Okay, good. Well, thank you very much, Amelia. That was a wonderful overview of a working group that is so active and that plays such an important role in our community. Thank you very much, Amelia, for doing all that.
Thank you, Irene.
Yes. If there are any comments or questions, I've seen already one question in the chat coming up. Maybe we can take that offline and present it actually in the, answer it in the chat and also in the Slack channel. I think that would be best in view of the time. So, but thank you very much, Amelia, for doing all of this, and all members, everybody here on the on this Zoom or YouTube meeting. Please take a look at our Springboard to Action. Yeah. Okay, now we move to a completely different aspect of our field, namely that astronomy is, of course, driven by our very largest telescopes, by the new data that we get from all of these instruments. And the IAU brings actually people together to make that possible and to optimize their use. So we are very pleased to have one of the chairs, David Spergel, formerly of the Flatiron Eye Institute, now president of the Simons Foundation, with us here today. Please start the recording.
Hi, I'm David Spergel. I'm the co-chair with Roger Davies of the Global Coordination from Ground and Space working group of the IAU. I want to apologize for not being able to join you in person, but do want to take this time to talk about some of the activities of our working group, which I view as sort of as an important part of the overall IAU effort of bringing the world community of astronomers together. And one of the things that we have focused on in the working group is serving as a neutral forum for discussions between different nations and multinational groups engaged in building large projects. And this is an incredibly exciting time in astronomy. We have lots of exciting projects across the spectrum led by countries all over the world. And one of our goals is to organize a series of focus meetings at each General Assembly and target workshop between General Assemblies. The Cobley Foundation has generally sponsored these as forums for bringing people together to talk. And in addition to talking about these large missions, our goals have also been to promote open data, archives available to all, and encouraging everyone in the world community to make their astronomical data available for all to maximize the science, or try to maximize what we as humans learn about the universe around us. To give an example of some of the things we've done, we had a very successful workshop back in 2017 in Leiden, looking at large telescopes from space and the optical IR and UV. There's lots of interest in this worldwide, talking about the science goals, how they might work together. This was a really terrific moment to bring together people from the world community interested in these large telescopes. In 2020, we had a transient workshop in Cape Town. Fortunately, this was in February 2020, when we were still able to gather together so easily, and this brought together a big community that transient science, I think, will be some of the most exciting science of the 2020s. There's a report on the archive that describes some of the recommendations of this transient workshop. And I think transient science really is a tremendous opportunity for world science, with many nations, including many emerging nations, able to make significant contributions to the panchromatic study of transients. Looking ahead, we will have a focus meeting in 2020 GA in Busan. We are going to be identifying topics for workshops scheduled between the GAs, either in 23 or 24. Probably hoping to help facilitate some presentations to the broader international community on the US Decadal Report, which we are promised will come out soon, and provide forums for disseminating other national or multinational plans and visions, and hope to work to identify new ways for involving emerging nations in these major national and international projects. So thank you, and hope to see you all in person in the coming years. Thanks.
Okay, thank you very much, David. That was a very short but comprehensive overview of the activities of another important working group that we have. And again, I encourage people to have comments on the Slack, also on some of the questions that David raised in terms of where to go next in terms of the planning for the meetings. Good. Then we turn again back to science. And the past triennium has been unusual in many ways. But one thing that I think nobody had expected is that we would have 6 Nobel Prize winners in astrophysics in this triennium. Jim Peebles, Michel Mayor, Didier Queloz in 2019, Andrea Ghez, Reinhard Genzel, and Roger Penrose in 2020. So warm congratulations to all. We are really so proud of all of you. And we are very honored to have us as live today, very early from California, Andrea Ghez. Andrea, we really appreciate you making the time for us to do this, and the floor is yours.
Thank you, Evine. It's a pleasure to be here and to share the work that we've been doing over the last 25 years. The original question that we set out to address is there a supermassive black hole at the center of our galaxy? And what we've been able to prove is that the answer is a resounding yes. At the center of the galaxy, we've created a laboratory now for understanding both the physics of supermassive black holes, understanding how gravity works in this extreme environment, as well as what role black holes play in the formation and evolution of galaxies. This project started when I first started my faculty job at UCLA. And I wanted to mention this, especially for the younger people, because in fact, our first proposal was turned down. We started off with a concept for a 3-year project. So I don't think we could have imagined still doing this 25 years later. What was challenging at the time is that the Keck telescope, where we've done all our work, had just opened up, and we were proposing to use the telescope in a new and different way. In other words, to get to the diffraction limit, which had not yet been achieved. Today, we've actually grown quite a bit from that initial team of 4. I'm sorry, I meant to mention that I really wanted to acknowledge my long-term collaborators, Mark Morris and Eric Becklin, in the original picture. And also shown was my very first graduate student, Beth Klein. Today, we're a team of roughly 24 people, where there are other core members who are incredibly important, in particular, Tuan Do and Jessica Liu. And we have become now a key science case for the development of technology at the Keck telescope, and then the future 30-meter telescope for the University of California. So this was quite an extension from that beginning of not being able to get telescope time. Now, there are 2 big picture perspectives on what makes this project interesting. One is to understand whether or not supermassive black holes exist, really to explore the physics, and today really testing Einstein's idea of general relativity, and then the astronomical role that black holes play. In the beginning, when we first started to announce our results, the thinking in the field was really which came first? Did the black hole came first, or did the galaxy come first? It was sort of a chicken or an egg question. And today we realize that these 2 things formed synergistically, that we have this intimate interplay between the relationship between the central black hole and its host galaxies. And in the center of the galaxy, we have an extraordinary opportunity to look at the feedback that exists between the central black hole and its host galaxy. Now, to appreciate this experiment, it's important to realize that there are 2 key technological advances that have really enabled this work to occur. The first is the advances in infrared detectors. Infrared measurements are essential in this work because we're looking at the center of the galaxy. And towards the center of the galaxy, there's a tremendous amount of extinction. In the optical, it's 30 magnitudes of extinction. But if you go to the infrared, that reduces to just 3 magnitudes of extinction. So being able to observe at infrared wavelengths, and in particular, to have very sensitive detectors so that our techniques for getting to the diffraction limit would work. So this is often the ignored aspect. So in fact, infrared detectors only achieved that level of sensitivity roughly 25 years ago. Similarly, another technology that is essential for this work to be possible is the ability to overcome the blurring effects of the Earth's atmosphere and to get to the diffraction limit of the very largest telescopes on Earth. For the first decade of this work, the technique was what I like to call poor man's adaptive optics. So it was a hardware simple and inexpensive, but computationally expensive technique for overcoming that blurring effects of the Earth's atmosphere. In other words, you just had to take very short exposures, and hence the need for very sensitive infrared detectors. Since that early era, the last 15 years or so, we've been able to get to the diffraction limit through a hardware complex and much more expensive, but much more powerful technique of adaptive optics, which in real times corrects for the distorting effects of the Earth's atmosphere and allows us to see the stars that are at the very heart of our galaxy and the ones that are really the key to this experiment. The way we approached the question of is there a supermassive black hole was to see the stars that were as close to where we thought the black hole was or is, and to look for the gravitational influence of the black hole on these stars. So it's a direct measurement that requires one to be able to resolve these individual stars. So we track today thousands of stars over a region that's actually quite a bit larger than what's shown here. But I want to draw your attention to this little box in the central arcsecond. These are the stars that are the key to this experiment. And the next animation, what I'm going to show you is actually a quarter of the real estate in this little box to really get a sense of what's going on. So this demonstrates that we weren't able to get to the diffraction limit. And this animation now shows how these stars have moved over the last 25 years. And this animation has gotten a lot complicated over these 25 years because our technology has evolved so much. So in the beginning with speckle imaging, you could get images with a single wavelength. So all you could do is to follow these stars and only the very brightest ones. So when stars are detected with an image, they're followed by a dashed line. And some stars pop up simply because once adaptive optics comes online, you can see stars that are much fainter. Once adaptive optics comes online, we can also, for the first time, take spectra of these stars. And the spectroscopy aspect has been incredibly important for this work. Spectroscopy not only allows us for the first time to get the third dimension of motion, so to see the velocity along our line of sight, but also we're able to pursue what kind of astrophysical stars these objects are, rather than treating them just like point particles. And I'll come to why that's so important in a moment. But for the moment, let's just think of these as point particles moving under the gravitational influence of a central object. Which is located where the star is, or I should say the asterisk for Sagittarius star, the radio source that was thought to be associated with the central black hole. These stars, you can probably see what my favorite star in the universe is. Its name is SO2. It's the one that has the most power for telling us what's at the center of the galaxy, simply because it's the one in which, for which we have complete measurements over its orbit, both from an imaging or an astrometry point of view, as well as a spectroscopy point of view. And it's this star that dominates our understanding of what's at the center of the galaxy. So at the beginning of this work, before we all jumped in with high resolution imaging, we knew that there was 4 million times the mass of the sun inside a region that corresponds to the size of the circle. But this circle is so big, so much bigger than the Schwarzschild radius of a supermassive black hole of that size, that it was hard to conclude that there was a supermassive black hole at the center of the galaxy. What this work has done has to show that this mass is actually confined to a volume that's a factor of 10 million times smaller than this original size. So we've shown that there's 4 million times the mass of the sun inside a region that corresponds to roughly the size of our solar system. So this has been an incredible leap forward in our understanding of supermassive black holes, moving the idea of supermassive black holes from a possibility to a certainty. And this is what has given us the strongest evidence to date for the existence of a supermassive black hole, not only at the center of our galaxy, but in fact, in any other galaxy in the universe. And this is what was recognized this year with the Nobel Prize. I wish I had a picture of Reinhard Genzel and myself together, but because this was remote, I'm showing you the one from the Crawford Prize ceremony. And I wanted to show this to really acknowledge that there's been two teams that have been hard at work over the last 2 decades on this project, and to really call out the benefit of competition. There's nothing like competition for keeping you on your toes. And also the two groups think differently about these measurements. And in fact, these measurements are quite hard. So there's something really beneficial for having a diversity of viewpoints to getting to the best science possible. So I'm really grateful for having had such competition, and I think science has really benefited from that. Now, moving forward, there still remains a tremendous amount of work to be done at the center of the galaxy. With the advent of adaptive optics, we, for the first time, could see what the nature of these stars that we were tracing were. And in fact, almost every single prediction for what we should see in the vicinity of a supermassive black hole has been inconsistent with these observations. So from my perspective as a scientist, this is like being a kid in a candy shop. There's so many questions that have arisen from this work. And just to give you a taste of a few of them, in this three-dimensional animation where we're pulling back from the center, those orbits we were looking at originally, the original prediction was that there should be no young stars at the center of the galaxy. And in fact, there were a few young stars outside that circle, which led people to say that the center of our galaxy couldn't possibly host a supermassive black hole. And that was the thinking in the late 80s. And yet, as we've gone closer, the dominant part of the population that we can see today are young. Those are the aqua blue stars that we see today. So the problem is that the tidal forces of the central supermassive black hole should overcome the self-gravity of any potential cloud at the densities that we see today. And this is not just a little problem, it's a tremendous problem because the densities are a factor of 10 to the 11th times smaller in the region that these stars exist than are needed to overcome through self-gravity, this tidal force. And there's been all sorts of ideas put forward for why these stars should exist. And you can see that one clue that has come out has been the existence of a common orbital plane that these stars reside in, suggesting that these stars presumably formed in a thick accretion disk, presumably somewhat like the disks that exist in active galactic nuclei in our galaxies. There are two other mysteries that I'll just briefly mention. We expect to see lots of old stars, and those are the orange stars. We see very few. The concentration of old stars is something that we use to find supermassive black holes in other galaxies. And yet in this case where we see a very clear example, there's very few old stars. And then the pink stars are the ones that are most intriguing to me these days. These are objects that are being tidally disrupted, torn apart. The first examples of being able to see spatially resolved tidal interactions with the supermassive black holes. And to get such interactions, one idea is that these are binary stars that have been driven to merge through the Kozai-Lidov interaction with the central supermassive black hole. So this may provide insight to why we're seeing gravitational wave sources at rates that are much higher than expected, and producing objects that are more massive than expected before. Now, I'll just close by saying that in addition to all these mysteries, we're also using these stars, in particular SO2, to investigate how gravity works near a supermassive black hole. And while some of the initial results, looking at things like the gravitational redshift have been completely consistent with what Einstein predicted, the second test, which we're in the middle of doing, which is looking for the precession of the periaps, is actually introducing yet again more surprises than answers. So this is something that we have not yet published, but we are seeing early evidence that in fact these orbits are moving in the retrograde direction, which would suggest the presence of dark matter in addition to the central supermassive black hole. So with that teaser, let me end by saying, if nothing else, I hope I've convinced you that we have extremely strong evidence for the existence of a supermassive black hole at the center of our galaxy. And this has introduced a wonderful laboratory for understanding both how gravity works and what role these black holes play in the formation and evolution of galaxies. Thanks for your attention.
Well, thank you so much, Andrea. Congratulations on a beautiful talk, and also one that is very instructive, I think, to many viewers around the world. Just looking at these orbits, it looks really like a Grand Central Station around there with all these stars whizzing around. And I'm sure that the new technology will give us even more clues to what is happening there. That's great. If there's any quick question, I think people are a little bit shy today, but I don't think they are that shy on the Slack. So if anybody wants to ask Andrea still a question or connect with her, then please do so through the Slack or through the chat. But thank you again, Andrea. We really appreciate that you got up this early for us to tell this wonderful story. Thank you. Good. Finally, we come to the end of today's whirlwind tour of the IAU, and we'll have a short presentation of the Office of Young Astronomers by the directors of the International School of Young Astronomers, the IAS, which have trained actually many students in developing countries over the last 50 years. Itziar from Mexico and David from Oslo. Welcome. Please go ahead.
Thank you so much, Evine. It is really a pleasure and an honor to be representing this very, very old program. As Evine mentioned, the program was launched in 1967, and we have had 42 schools that are devoted to graduate students around the world, but basically targeting those that are in isolated type of conditions, whether in developing countries or just in remote universities. And I'm starting this presentation with our last school, a photograph from graduation day of our last school, where you can see 39 participants that came to work together with 16 lecturers from around the world in 3 very intensive working days for their formation, for promoting the advancement of their master's and PhD studies. And just to complete this picture, I am also going to present a photograph from the 8th school in 1977 in Brazil, where you can see the same happy faces of students working together and coming together many times for the first time in an international environment. This is our office. David and myself are volunteers to this program. We are not paid for this work. And we have a steering committee that basically supervises and basically helps us in organizing this program. We come together with local directors in interested host countries to bring this program to the regional area where the local host country is going to host the school. So target population, isolated MSc and PhD students. We have the goal to broaden the participants' perspective on astronomy, and the lectures are well known and spread within the world experts on their topic. And you can see to the right photographs from Colombia, Egypt, and Ethiopia of again the graduation picture. So what are the benefits for the students? Certainly, they have contact with international lecturers. They complement their basic astronomical background. They have access to quality notes. They practice tools that we usually work with for research, but they might not have been introduced to them. They have some observational experience. We give them mentoring when needed. And they create a network with fellow students to develop into the next generation astronomy professionals in the region. All of these things really we have come into a challenge with the current pandemic situation. And we haven't had any school since 2019, and we are hoping to just restart the organization of this school soon. So our target population, in order to explain it, this is a diagram we like to show. On the top, you can see countries where the school has been hosted. Again, the school is hosted in a country, and that school serves the region, not only the country where it is hosted. And our main target for the students that we recruit for the students can be explained in this diagram, where we see the individual membership in the IAU per population and the number of individual members in the country. And so we are targeting basically countries which are in this diagram here. In the bottom of this diagram, the main targets certainly are those that have very small communities of professional astronomers and also have small communities with respect to the general population of their of the country. This is the distribution of alumni. We have had over the years a little bit less than 1,500 students from 94 countries, 42 schools over 54 years. And in here you just can see with different colors students that have been drawn from the different countries. There is a correlation where students mostly come from one country because that country has volunteered to host one of the schools more often than others. And this is a small gallery of people that have come through the schools over the years. Recently, we have launched both a request for testimonials of prominent astronomers doing amazing research, serving their communities through the national coordination efforts, both for the IAU, for the educational program of the IAU, for the outreach program of the IAU, etc. And you can see astronomers that are both serving as people responsible for working groups and for divisions, and people working in their countries, like the top row of astronomers, or people just working in other countries, like Alfonso Aragón Salamanca, José Ramón Valdés, or Julio Navarro, who just came from one of these highlighted regions and now work in other countries. So from all these testimonials, we would like to highlight just one of them because we don't have the time for it. So we just chose Somaya Saad from Egypt. She was a student in 1994. She was the local director of one of the schools in 2018 and now serves as the national contact for Egypt. And she highlights her experience in the schools as first, how this basically was able to create the faith and self-confidence and training for astronomy, how she learned the goals of equality and diversity and the concept of non-bias to work with groups around the world, and third, how she learned to care for the youth, and that the young people is our future as a community. And we have beautiful testimonials from all the other people that have participated in our service. We actually have launched an online survey before the summer, where you can see that most of the students say 92% that they benefited from participating in the school. They could strengthen their research, and they did develop a network through this experience. So the future is pending on pandemic development around the world. We had the schools from 2020 and 2021 being postponed to 2023, South Africa and Algeria. We are lobbying for 2022. So if there is anybody out there, please contact us. We have this official address, isia@iso.org, where you can contact us and we can plan together for the next schools in this program. Thank you.
Thank you very much, Itziar. Wonderful to see here all the results and the success of ISIA over so many years now. And you see indeed how people have been able to make their career and grow through this structure. Wonderful to see this. And thank you very much both to you and David for all the work that you're doing, because I've seen in person how much work it is. Much appreciated. Good. Well, this ends the taster, the pre-program. It's time that we now sign off from